When we take up the topics of scatterplots and correlations, we're taking up a situation where we have two variables, as we have for the last few topics, but in this situation, both of the variables are being measured on an interval or ratio scale. They're continuous variables, things like height or weight or temperature or salary or many of the things that we measure in medical settings. So we'll look at these both as we graph them and also as we compute a number to represent their relationship. Although the word correlation in general simply means the relationship between two or more variables, most of the time when researchers use that term, they're referring to the Pearson product moment correlation. It's a statistical measure, a single number that describes that relationship, and it in fact tells us both the strength and the direction. The Pearson product moment correlation can only be computed for interval or ratio level data. The most common first step before computing a correlation coefficient is first to look at the data in a scatter plot, and that's what we'll do now. In general, scatter plots show two variables at the same time. On the horizontal axis, we're looking at what we call the x variable, and it's usually the one that is the independent variable or the predictor variable. And on the vertical axis, we're looking at the y variable. It's usually the dependent variable or the outcome variable, the thing that we're trying to explain. And there's several things that we can look at when we plot cases according to their value on the x variable and on the y variable. And one of the first things that we look for is whether there's a positive or a negative association. In a positive association, as the value of the x variable gets larger, so does the value of the y variable. In contrast, a negative association usually means that as the x variable gets larger, the y value in fact gets smaller. Our correlation coefficient represents that trend or direction in terms of the sign that's used. A positive correlation, where increasing values of x are related with increasing values of y, will end up with a positive correlation, something that's greater than 0. On the other hand, a negative, sometimes also called an indirect correlation, where one of the variables decreases as the other one goes up. For instance, if you think about the amount of time you spend in a weight loss program and your overall weight, the longer you're in the weight loss program, the less your weight is. That would be a negative or indirect correlation, and it would show up with a negative correlation coefficient. The points in our scatter plot can either be tightly clustered along a line or else they can be pretty loosely clustered. When they're tightly clustered, at any particular x value, there's really only a small range of y value points available. In contrast, when they're not very tightly clustered, for any particular x value, there's quite a range of y value points that are available there. When the points are tightly clustered along the line, we call it a strong relationship. If I know quite a bit about your value on the x score, it means I can predict your y score pretty accurately. And the correlation will be close to +1, or else it will be close to -1. A weak correlation, on the other hand, is one that's much closer to 0. And in the middle, we have mid-range correlations, anything that goes from 0 up to 1 or from 0 down to -1. One of the reasons that we use scatter plots is that there are circumstances in the data that might make the coefficient that we compute a less accurate or even an inappropriate way of measuring the relationships. And some of these are listed on the slide: nonlinear relationships or uneven scatter or outliers and clusters. When people encounter these in the data, they usually report it in the research. Sometimes they take special techniques and explain that in their methods section. Other times they simply report that this problem was there and that because of the problem, the correlation coefficients might be taken with a grain of salt. And we'll see what those look like in the actual scatter plots. The Pearson product moment correlation computes the measure of strength along a straight line. And as you can see in the picture on the left, the points are not perfectly along the line, but they're pretty much in a linear direction, compared to the picture that we see on the right, where the first part of the points go upward, but then the second part of the points almost take a different trajectory and are moving downwards. We call that a curvilinear relationship. The correlation coefficient, instead of being able to plot those two parts equally, would probably take and put one sort of averaging line through it, and it would be too low for the first half of the points and then too high for the second half of the points. So that would be a situation where the correlation coefficient is not a good representation of the data. Similarly, our correlation coefficient expects that for every value of x, there will probably be about the same amount of variability in y. They call that homoscedasticity, and it basically means that the scatter is about the same no matter what the x value is. When that assumption is violated, when you have a low level of scatter at one part of the distribution and a much higher level of scatter at a different part of the distribution, the correlation coefficient averages it but doesn't tell us that at one end the relationship is strong and at the other end the relationship is really quite weak. So again, the correlation coefficient by itself is not the best choice when we have heteroscedasticity. An outlier is one or a few points that are distinctly different from the trend that are visible in the rest of the data. And the problem with the outliers is that they get into the equation for a correlation and they shift things, so that rather than calculating a correlation around a line with a slope that's pretty steep, they'll probably calculate a correlation that takes that into account that outlier much more than it should. So the overall correlation number has been shifted towards that outlier and therefore is a bad representation of the other points of data in the data set. Sometimes, even though the data seem to have been gathered in a single place, they may end up with clusters in the data, and those clusters may even have different trends. In the ones we see on the screen, the ones that go with a larger value of x seem to have a positive trend, while there seems to be a negative trend in the data that are at the lower end of x. And yet if we saw these as a single sample rather than as two different groups, we would probably get a correlation coefficient that would plot along a positive line and would completely erase the fact that the data seem to be in two clusters. So this sort of thing, when we see it in the plot, also lets us know that we probably should not just compute the correlation coefficient and go on. Once we've decided on the basis of the scatter plot that it is legitimate for us to go ahead and compute the correlation coefficient, we're going to end up interpreting it in terms of three things: the direction, the strength, and the shared variability between the two variables. The scatter plots on this page come from the Guess the Correlation website, which is linked in the course, and I encourage you to use it. It's a website that lets you visualize correlations and begin to get a sense for how the number of the correlation coefficient corresponds to the strength of the relationship. Here we see almost no relationship, just sort of a ball of points in the lower left, some relationship in the second one on the left, more of a relationship, although a negative one, and the lower right, and the strongest relationship in the tight cluster of points along a line in the upper right. When you go to the website, you'll see 4 correlations like this, and it always gives you the possibility of choosing among the options. Sometimes the options can be quite hard to detect. For instance, minus 0.84 and minus 0.94 are going to be pretty similar graphs. They're both negative. Here's our strongest correlation, probably the 0.94, but you can see that the minus 0.84 is not really all that different. So one of the benefits of using the Guess the Correlations website is getting increasing expertise at recognizing and knowing about how much correlation you would see once you've computed the coefficient out of a set of points in a scatter plot. Before we compute the correlation, it's also worthwhile to just ask ourselves about how strong a correlation do I actually expect here. And we can see 3 different situations on this set of graphs. We really would not expect much correlation between shoe size and IQ because they just are determined by completely different sets of variables. So the data that we see are not surprising. We see sort of a round ball with no particular relationship because we expect almost no particular relationship. On the other hand, IQ scores are probably related at least somewhat to GPA, but as we've seen from studying Carol Dweck's mindset information, we also know that there's a possibility of basically growing your intelligence and your skills through effort, and so we expect to see some variability and not pure determination. On the other hand, something like your annual salary relative to your monthly salary is almost one-to-one correspondence. Short of variability due to bonus pay, if I know your annual salary, I can predict your monthly salary and vice versa. So I've got no relationship, a moderate relationship, and a strong relationship shown in these graphs. The correlation coefficient can also be seen as a way of measuring shared variability. So it's looking at how much of the variability in one variable is shared with a second variable. For instance, how much of the variability of your height is shared with your weight. If we're looking at a sample and one variable does not vary, if it's a constant, for instance, if everybody in my study were exactly 6 feet tall, then it cannot co-vary with any other variable, and the correlation will be 0. If I had a bunch of people who were all 6 feet tall, but they weighed different amounts, there would be no correlation between their height and their weight because their height was all the same, but their weights varied. So if the range of variability is constrained, if either the very high or the very low scores are artificially cut off, that's going to have the impact of reducing the value of our correlation coefficient. This scatter plot shows how that kind of restraint can have an impact. If I were having access to the full range of the data, I would generally see a positive relationship. But if somehow my sample were only able to pick up people at the high end of the X scale, at that end I see pretty much no relationship. I just get a ball of points. This might happen if my sample were drawn only from people who qualified for some situation. If that line in the middle were a cutoff and I was not seeing the full range of the independent variable, I might miss the actual relationship in the data because I'm only seeing a restricted range. The computations in this set of graphs show us just how dramatic the impact of an outlier can be. In this little data set of 5 points on the left-hand side, I've got a very, very low correlation, 0.08, which is close to 0, and means that these 5 points show almost no relationship of the x and y variables. On the right-hand side, the same 5 points are there, but 1 point has been added, an outlier that's very high up and to the right. And notice that the addition of that one point gave me an incredibly strong correlation of 0.85. So this is just one example of how an outlier can really shift the value of the correlation coefficient. In fact, that 0.85 correlation on the right is a poor representation of most of the data, which are lower on both the x and the y values. The shared variability is also called sometimes the coefficient of determination, or r squared. And this is, in fact, the same r squared concept that we've had in our measures of effect size. We're talking about the proportion of variability that's shared by the two variables, or another way of saying it, how much of the variability in the dependent, or y variable, can I predict if I know the value on the x variable. So this is very similar to the r squared that we had in t-tests, and we'll see that it's similar also to the eta squared that we had for our analysis of variance tests. A thing to notice is that the correlation coefficient doesn't really increase in a linear manner. And we can see in the graph over here on the right-hand side that as the correlation coefficient goes up in steps of a tenth, from 0.1 to 0.2 to 0.3, up towards the maximum correlation of 1.0, that the coefficient of determination, the proportion of shared variability, goes up exponentially, goes up as squares. So when I go from 0.1 to 0.2, I'm going from a coefficient of determination of 0.01, 0.1 squared, to 0.04, which is 0.2 squared. And it's not a very high line. But if I go further out, if I go to the movement from 0.7 to 0.8, you can see that the amount of increase is much greater. This slide gives you an overall framework for interpreting a correlation. It lets us know the meaning of positive and negative correlations, and then for each number it gives us some language to use as we describe the relationship. Is it very weak, weak, moderate, strong, or very strong? The use of the terms strong and weak is relative in part to the domain that we're in. Most things that are about human beings, whether they're biological or especially things that are social, tend to have lower correlations. Human beings are just highly variable in a lot of ways. If I were looking at the relationship of weight and size in something being done in a factory or a mechanical relationship, I might expect a large number of strong correlations because elements like wood or steel tend to be much less variable than human beings. Over on the right-hand column, the correlation coefficient that's in the left-hand column is being translated into that coefficient of determination. And you can see that even for that very strong relationship of 0.8, it's really a little bit less than 2/3 of the variability, 0.64 or 64%, that is shared between the two variables. The textbook does give us all of the equations for computing correlations and tries to demonstrate to us that beginning with raw scores is probably the best way to go because we don't have to compute so many different parts. In fact, in this course we take the point of view that the best way to go is to use a computer. Any of the methods that are demonstrated in the book would involve pushing calculator buttons so many times that the possibility of doing an error is so great it's not worth doing. So in this course we're only going to do the computations using a computer, but we will look at the equations to increase our understanding of how the correlation coefficient operates. The basic notion of our Pearson correlation coefficient is that it's a ratio that measures the degree and the direction of linear relationship between two variables. Their covariability, or their variability with each other, is in the numerator of the relationship, while their independent variability is in the denominator. The equation for the numerator is often called SP, or the sum of the cross products. It's similar to the sum of squared deviations from the mean that we've seen before, but rather than having one variable, we have two variables. So instead of squaring deviations from one mean, we take each point and take its x value and find its deviation from the mean for x, and then we take its y value and find its deviation from the mean value for the mean of y, and we multiply those two things together. Just as when we would compute the sum of squared deviations, if both of those values are negative, we'll get a positive number. But unlike the sum of squared deviations, there is the possibility that one of these might be a positive number and one might be a negative number. When that happens, a positive times a negative equals a negative number, and so if we have that happen a large number of times, when we add it all together with that summation sign, we would end up with a negative value for SP, and that's where we get the negative value of a correlation. Overall, our correlation coefficient is that sum of the cross products in the numerator divided by the square root of our sums of squares. Remember, that's the variability for each of our variables. So we've got the sum of squared deviations in x and in y multiplied together. So this is the co-variability, and this is the separate variability in the denominator. As our textbook points out, it is also possible to compute our R correlation using z-scores. However, in this course, we're not going to do the computations. The important thing to know is going to be the fact that we saw in the previous slide, that the best way to think of correlation is with covariability in the numerator of a ratio and separate variability in the denominator. One of the most famous statements that anyone who has ever taken a statistics course has heard is that correlation is not causation. Correlation tells us that two things are related. Causation is a much stronger statement. To say that one thing causes another requires that we have an experimental method, something that is controlling all of the important other reasons that might cause the relationship. So for instance, to demonstrate causation, I have to prove that the thing I call a cause happened before the result. But the most serious search, and the one that's most difficult, is the search for spuriousness, a third variable that might be causing both of the related variables. So examples include the fact that the number of fire trucks who go to a fire is an excellent predictor of how much damage is done at the fire. The problem is that both variables, the dollars of damage and the number of fire trucks, are probably related to the size and the seriousness of the blaze. Lots of things that we see correlated have that characteristic. We see things that often crime rates go up in the summer, and so do ice cream sales, and so people have said that maybe ice cream causes crime. But in fact, of course, with heat, more people buy ice cream and more people are out on the streets. So whenever we see that two things are correlated, all we know is that they vary together. Before we can talk about causation, we need either experimentally or statistically to control for the impact of other variables that might in fact be generating both of the situations we're looking at and causing the correlation to occur. Correlations are a powerful technique and one of the most commonly used because many people find them easy to understand. I encourage you to carefully study the module Pitfalls of Correlations that's in the textbook. It does an excellent job and provides several good examples to help you avoid falling into logical and research-based errors. You'll see them around you every day, but having taken this course, you have the opportunity to be statistically savvy and avoid the pitfalls yourself.